let's talk about something really exciting today. How we can make sense of ridiculously large and complex data. Ever looked at a massive spreadsheet and thought, yeah, I have no clue what's going on here? That's where dimensionality reduction comes in. And one of the coolest techniques out there is Sammon mapping. Picture this. You're in a new city, lost, and all you have is a detailed map with 1,000 roads and landmarks. Too much detail, right? What if someone gave you a simplified map that only showed the key locations, making it much easier to navigate? That's exactly what Sammon mapping does with data. It takes high-dimensional chaos and translates it into something more understandable while preserving essential relationships. What makes this technique special is that it doesn't just randomly squash data into a smaller space. It carefully preserves distances between points, making sure that things that were close together in the original space stay close together in the mapped space. And that's huge for things like image recognition, data clustering, and even complex pattern detection. But here's the real kicker. Sammon mapping isn't just a visualization trick. It's a gateway to deeper data insights. The way it rearranges data points can reveal hidden patterns and structures that might have been impossible to spot in a raw dataset. That's why it's widely used in machine learning, bioinformatics, and even financial analysis. So, how does it actually work? What makes it different from other dimensionality reduction techniques like PCA or t-SNE? Stick with me because in the next section, we're going back in time to see where this all started and how it evolved into what it is today. To understand why Sammon mapping is such a game changer, we need to rewind to 1969 when John Sammon introduced this technique to the world. Back then, the world of data analysis was growing fast, and researchers were searching for ways to make sense of high-dimensional data without losing essential information. Sammon's breakthrough was in developing a way to preserve relative distances between data points while reducing dimensions. But here's the fun part. Sammon mapping didn't just pop up out of nowhere. It was built on the foundations of earlier multidimensional scaling techniques, which were originally used in psychology and sociology to map out human perceptions. Yes, that's right. The same principles that help analyze human behavior were adapted for complex data problems in fields like machine learning and bioinformatics. Over the decades, as computational power increased, Sammon mapping became more practical. Researchers refined the optimization process, improving how data points are repositioned in a lower dimensional space. More efficient algorithms, better hardware, and advanced statistical techniques all played a role in making this method more accessible and useful in real-world applications. One of the key milestones in the history of Sammon mapping was its adoption in bioinformatics, where scientists use it to visualize gene expression data. By mapping genetic relationships, researchers can identify patterns that help in disease diagnosis and treatment plans. And let's not forget finance. Portfolio managers use similar techniques to analyze stock market trends, clustering assets with similar risk profiles. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Now that we know where Sammon mapping came from, let's break it down into its core components. What exactly happens when we apply this technique to data? What are the moving parts that make it all work? First, there's the idea of dimensionality reduction. The main goal here is to take data from a high-dimensional space, where it might have hundreds or even thousands of variables, and project it into a space with fewer dimensions, typically 2 or 3, while preserving meaningful relationships. But how do we know what's meaningful? That's where pairwise distances come into play. In high-dimensional space, every data point has a relationship with every other point. Some are close together, others are far apart. Sammon mapping ensures that these distances remain as consistent as possible when the data is projected onto a lower dimensional space. Another crucial concept is geometric relations. In simple terms, we're trying to maintain the shape of the data even as we shrink it down. If a cluster of data points forms a particular pattern in high dimensions, We want that pattern to still be recognizable after mapping. And we can't forget data projection, the actual mathematical transformation that takes our original data and places it into a new, lower dimensional space. Unlike principal component analysis, PCA, which focuses on maximizing variance, Sammon Mapping prioritizes maintaining the original distances between data points. Each of these components plays a crucial role in ensuring that Sammon Mapping creates a useful and accurate representation of high-dimensional data, but how does it all come together mathematically? That's what we'll dive into next as we explore the mathematical foundation behind Sammon Mapping. Now, let's get into the nuts and bolts of how Sammon Mapping actually works. This is where things start to get really interesting because we're diving into the mathematical framework that makes this technique so powerful. At the core of Sammon Mapping is an optimization process designed to preserve the structure of the original dataset. The key idea is to minimize a stress function, often called the Sammon stress function, which quantifies the difference between the original pairwise distances in high dimensional space and the new distances in the lower dimensional projection. Here's how it works. First, we calculate the pairwise distances between all data points in the original space using a chosen distance metric, typically Euclidean distance. Then we place those points in a lower dimensional space and adjust their positions iteratively using gradient descent. The goal is to minimize the difference between the original and projected distances, ensuring that close points stay close and distant points remain distant. This optimization is tricky because the stress function is nonlinear, meaning it doesn't have a straightforward solution. Instead, we rely on iterative approaches to nudge the data points into their best possible positions. One common approach is using Newton's method, which helps refine the placement of points for a more accurate projection. A critical part of this process is selecting the right initial conditions. A good starting configuration can significantly impact how well the optimization converges, making the final mapping more accurate and stable. Understanding these mathematical foundations is essential for anyone looking to apply Sammon Mapping effectively. But once we have the theory down, how do we actually implement it step by step? That's exactly what we'll cover next. Now that we understand the theory behind Sammon Mapping, let's talk about how to actually implement it step by step. First, we start with data preparation. This means cleaning the data set, removing outliers, and handling missing values to ensure a smooth process. Garbage in, garbage out. So this step is crucial. Next, we calculate pairwise distances between all data points using an appropriate metric like Euclidean distance. This step is the foundation of the mapping process because the entire technique revolves around preserving these distances. Once we have our distances, we initialize the lower dimensional representation, often with random placement or using another dimensionality reduction technique as a starting point. The closer this starting position is to the optimal layout, the better the final result. Then we apply the optimization algorithm, typically gradient descent, to iteratively adjust the positions of the data points. The goal is to minimize the stress function, ensuring that the mapped distances closely match the original. Finally, we interpret the results. This means visualizing the final lower dimensional representation and assessing whether it accurately captures the relationships in the original data. To refine this process, different strategies can be used, such as adaptive learning rates, tuning hyperparameters, and experimenting with alternative distance metrics. Each of these choices can affect the final mapping quality, making implementation both an art and a science. Now that we have the implementation steps, the next question is, where can we actually use this technique? That's what we'll explore next. Now that we know how to implement Sammon Mapping, let's explore where it's actually used. One of the most fascinating applications is in image recognition, where high-dimensional pixel data is transformed into a lower dimensional space to reveal meaningful patterns. Imagine you have thousands of images, each containing intricate details, textures, and structures. The raw pixel data exists in an incredibly high-dimensional space, making it almost impossible for a human or even a traditional algorithm to interpret efficiently. This is where Sammon Mapping shines. By projecting the data into a more digestible form, it helps classify and cluster images based on their intrinsic features. A great example is facial recognition. When training a machine learning model to recognize faces, every image is composed of thousands of pixels, each with its own color and brightness values. Without dimensionality reduction, this data is too vast to process efficiently. Sammon mapping helps compress this information while preserving important facial features, enabling better identification and clustering of similar faces. Another powerful application is object detection. Say we want to differentiate between different types of vehicles in traffic surveillance footage. Raw images are mapped into a lower dimensional space while keeping similar objects close together. This helps AI models distinguish between cars, trucks, motorcycles, and buses based on structural similarities rather than raw pixel comparisons. Salmon mapping also plays a huge role in medical imaging. In MRI scans, X-rays, and CT scans, the amount of data generated is immense. Doctors and researchers rely on advanced visualization techniques to spot anomalies, detect tumors, and analyze organ structures. Salmon mapping helps condense this high-dimensional medical data into meaningful visual representations, making it easier to interpret and analyze. But this is just the beginning. The real question is, how does salmon mapping compare to other techniques like PCA or t-SNE? Does it always provide the best results? Or are there cases where other methods might be more suitable? That's what we'll explore next. Now let's put salmon mapping head to head with one of its biggest competitors, principal component analysis, PCA. Both techniques aim to reduce dimensionality, but they take very different approaches, and that has major implications for their applications. PCA is like a spotlight. It focuses on maximizing the variance in the data. It identifies the most significant axes in high dimensional space and projects the data onto those. This makes PCA incredibly effective when we want to retain the overall structure of the data while reducing noise. It's computationally efficient, easy to implement, and widely used in data pre-processing, finance, and even neuroscience. Salmon mapping, on the other hand, is more like a finely tuned sculptor. It works by preserving the pairwise distances between data points rather than emphasizing variance. This means that if your data has nonlinear structures, salmon mapping can capture and maintain these relationships much better than PCA. However, this also makes it more computationally expensive and dependent on good initialization. So when should you use PCA and when should you opt for salmon mapping? If you have a dataset where variance explains most of the structure, like financial stock movements or sensor data, PCA is often the go-to choice. It's fast, scalable, and works great when you just need a simplified representation of the data. However, if your dataset contains complex, nonlinear relationships like biological sequences, facial recognition, or clustering problems, salmon mapping can give you a much more accurate, lower dimensional representation. The trade-off is that it takes more computation and requires careful parameter tuning to get the best results. One major limitation of PCA is that it assumes linearity, meaning it won't always work well for data sets with curved manifolds. Salmon mapping doesn't have this limitation, but it may struggle with large data sets due to its iterative optimization process. And then there's the middle ground, other techniques like t-SNE and UMAP, which offer nonlinear dimensionality reduction with different trade-offs in computation and interpretability. So where does salmon mapping truly shine? in situations where we need a more faithful representation of complex data structures, particularly when pairwise relationships are crucial for interpretation. But if you need something fast and robust for general purpose dimensionality reduction, PCA is often the safer bet. In the next section, we'll take a closer look at the strengths and weaknesses of Sammon mapping, because while it's powerful, it's not perfect. What are its limitations and how can we work around them? Let's find out. Now that we've compared Sammon mapping with PCA, let's dive into its strengths and weaknesses. No technique is perfect, and while Sammon mapping is incredibly useful, it does have its trade-offs. Let's start with the strengths. One of the biggest advantages of Sammon mapping is its ability to preserve pairwise distances. This means that it maintains the true relationships between data points, making it great for visualizing clusters and complex structures. Unlike PCA, which can distort the shape of data when reducing dimensions, Sammon mapping ensures that proximity between points remains accurate. Another advantage is that it's nonlinear, meaning it can handle curved manifolds and datasets with complex relationships. This makes it especially useful for applications like image processing, medical imaging, and genomic data analysis, where linear techniques like PCA might fail to capture important structural information. However, there are some limitations. One of the biggest challenges is that Sammon mapping is computationally expensive. Unlike PCA, which has a closed-form solution and can be computed efficiently, Sammon mapping relies on iterative optimization, which makes it slow for large datasets. If you're working with millions of data points, this technique may not be the best choice. Another advantage is that it's nonlinear, meaning it can handle curved manifolds and datasets with complex relationships. This makes it especially useful for applications like image processing, medical imaging, and genomic data analysis, where linear techniques like PCA might fail to capture important structural information. However, there are some limitations. One of the biggest challenges is that Sammon mapping is computationally expensive. Unlike PCA, which has a closed-form solution and can be computed efficiently, Sammon mapping relies on iterative optimization, which makes it slow for large datasets. If you're working with millions of data points, this technique may not be the best choice. So, where does this leave us? Sammon mapping is an excellent tool when distance preservation is crucial, such as in clustering and complex data visualization. However, for large-scale, high-speed applications, other methods like PCA or t-SNE might be preferable. But what about the future? Are there ways to improve Sammon mapping to make it more scalable and efficient? That's exactly what we'll explore next. To truly understand the impact of Sammon mapping, let's look at a real-world case: medical imaging. One of the biggest challenges in medical diagnostics is analyzing large-scale imaging data while retaining critical spatial relationships. Sammon mapping has been used in MRI and CT scan analysis to reduce dimensionality while preserving the spatial distance between critical regions of interest. For example, researchers analyzing brain scans can use Sammon mapping to detect patterns related to neurological disorders. By reducing the complexity of the data without losing essential relationships, it becomes easier to distinguish between normal and abnormal brain structures, helping in early detection of diseases like Alzheimer's and Parkinson's. Another use case is tumor classification. High-dimensional radiology scans contain vast amounts of pixel and voxel information, making direct analysis difficult. By applying Sammon mapping, researchers can visualize how different tumor types cluster based on molecular composition and structural similarities, improving classification and treatment planning. In cardiology, Sammon mapping has been used to study heart anomalies through echocardiograms and MRI scans. By reducing high-dimensional data while maintaining structural integrity, doctors can identify irregular heart patterns and potential risks more efficiently. Medical imaging is just one of many fields where Sammon mapping has made a significant impact. But what about the future? Are there new frontiers where this technique could revolutionize data analysis? That's exactly what we'll discuss next. As technology progresses, so do the tools and techniques that power complex data analysis. Sammon mapping, despite being developed in 1969, has not remained static. It has evolved alongside advances in computational power, optimization algorithms, and data science applications. One of the biggest advancements is algorithmic optimization. Originally, Sammon mapping relied on computationally expensive iterative methods like gradient descent, which required careful parameter tuning. Today, researchers have integrated adaptive learning rates, stochastic gradient descent, SGD, and second-order optimization methods to make the process faster and more stable. These improvements help avoid local minima and ensure better convergence. Another breakthrough comes from parallel processing and GPU acceleration. Back when Sammon introduced his mapping technique, computation was limited by single-core processing. Now, with the rise of multi-core CPUs and powerful GPUs, large-scale data transformations can be executed much more efficiently. Parallelization of Sammon's optimization function has reduced execution times significantly, making it feasible to apply this method to millions of data points. Then there's hybrid approaches where Sammon mapping is combined with other dimensionality reduction techniques like PCA, t-SNE, and UMAP. In many applications, PCA is used to first reduce the data to a manageable size before Sammon mapping is applied for finer adjustments. This hybrid strategy maintains both variance and distance preservation while improving computational efficiency. We're also seeing the integration of deep learning and Sammon mapping. Researchers are exploring how autoencoders, neural networks designed for dimensionality reduction, can work alongside Sammon mapping to enhance feature extraction. By leveraging deep learning's ability to uncover hierarchical features, Sammon mapping can refine its representation in ways that were previously impossible. Finally, real-time applications are emerging. With improved computational power and algorithmic efficiency, Sammon mapping is now being used in real-time systems, from fraud detection in finance to anomaly detection in cybersecurity. The ability to quickly reduce dimensionality while maintaining relationships between data points is proving invaluable in high-stakes decision-making environments. The future of Sammon mapping is exciting, but challenges remain. Can we make it even more scalable? Can we develop automated tuning methods to optimize its parameters dynamically? Those are the frontiers that researchers are pushing toward. So, what's next? What hurdles still need to be overcome for Sammon mapping to reach its full potential? That's exactly what we'll tackle in the next section. Despite its many advantages, Sammon mapping is not without challenges. One of the most significant limitations is computational complexity. The optimization process is iterative and time-consuming, making it difficult to scale for very large datasets. Unlike PCA, which can handle massive datasets with ease, Sammon mapping struggles with efficiency as data size increases. Another major hurdle is sensitivity to initialization. The algorithm requires a good starting configuration, and if the initial placement of points is poor, the optimization may get stuck in local minima. This can lead to suboptimal mappings that do not accurately preserve the original relationships. Researchers have attempted to mitigate this by using alternative initialization techniques, such as random projections or pre-reducing dimensionality with PCA before applying Sammon mapping, but the issue persists. Additionally, parameter tuning is often required. The choice of learning rate, stopping criteria, and distance metrics can significantly impact performance. Unlike other techniques that offer more straightforward parameter selection, Sammon mapping requires careful adjustment to get the best results. Many users find themselves experimenting with multiple configurations before finding an optimal setting, which adds to the computational cost. Another crucial issue is scalability. Since Sammon mapping requires pairwise distance computations, memory and processing demands grow quadratically with the number of data points. This means that applying Sammon mapping to datasets with millions of observations becomes infeasible without significant modifications, such as mini-batch processing or approximations that reduce computational overhead. There's also the challenge of interpretability. While Sammon mapping effectively reduces dimensionality and maintains distances, it does not provide clear insights into which features contribute most to the final representation. Unlike PCA, which provides eigenvectors that explain variance, Sammon mapping produces a transformation that is difficult to decompose into meaningful individual contributions. Beyond these technical issues, comparability with other methods remains a topic of debate. While Sammon mapping is effective at preserving distances, newer methods like t-SNE and UMAP have gained popularity for their superior performance in certain applications. t-SNE, for instance, is particularly useful in clustering applications where local structures matter more than global distances, while UMAP offers both local and global structure preservation with faster computation times. Finally, real-world application constraints pose another set of challenges. In fields such as bioinformatics, medical imaging, and finance, practitioners require not only accurate but also interpretable and scalable solutions. If an algorithm is computationally expensive and requires extensive fine-tuning, it may not be adopted widely despite its theoretical advantages. Given these challenges, what are the future directions for improving Sammon mapping? That's what we'll explore next. While Sammon mapping faces several challenges, the future holds promising opportunities for improving and expanding its applications. Researchers are actively working on refining the algorithm, making it more scalable and efficient for large datasets, and integrating it with modern machine learning techniques. One of the most exciting areas of development is hybrid approaches. Combining Sammon mapping with other dimensionality reduction techniques like PCA, t-SNE, or autoencoders has shown potential for improving both speed and accuracy. For example, PCA can be used as a pre-processing step to reduce initial dimensionality, making Sammon mapping's optimization more efficient. Another promising direction is adaptive optimization techniques. Traditional gradient descent methods can be slow and require fine-tuned learning rates. However, advances in optimization algorithms, such as adaptive momentum-based methods and stochastic gradient descent variants, could significantly improve convergence speed and prevent the algorithm from getting stuck in local minima. Researchers are also exploring ways to parallelize the Sammon mapping optimization process. Given the rise of high-performance computing and GPU acceleration, distributing the computational workload across multiple processors could make it feasible to apply Sammon mapping to much larger datasets. This would open the door for real-time applications in fields like finance, cybersecurity, and big data analytics. Additionally, deep learning integration is an exciting frontier. By embedding Sammon mapping into neural networks, researchers could develop models that learn optimized lower dimensional representations in an end-to-end manner. This could be particularly beneficial in fields such as bioinformatics, where high-dimensional genetic data needs efficient feature extraction for classification tasks. Another critical area of improvement is automated parameter selection. One of the biggest bottlenecks of Sammon mapping is its reliance on manually tuned hyperparameters. Implementing self-adjusting mechanisms that dynamically optimize parameters based on dataset characteristics could make the technique more user-friendly and broadly applicable. Finally, as the need for interpretability in AI grows, efforts to improve visualization techniques associated with Sammon mapping are underway. Interactive visualization tools that allow users to explore mappings dynamically could make the technique more accessible to non-experts in machine learning. The future of salmon mapping is filled with possibilities, and as computational power continues to increase, its limitations will likely become less significant. The real question is, how will these advancements shape the way we use salmon mapping in the years to come? That's something researchers and data scientists will be exploring in the near future. Now that we've explored every facet of salmon mapping, let's wrap up with the key takeaways: purpose and importance. Salmon mapping is a powerful nonlinear dimensionality reduction technique that preserves the pairwise distances between data points. This makes it highly effective for visualizing and analyzing high-dimensional datasets, where maintaining relative distances is critical. Key strengths: it excels in areas such as image recognition, medical imaging, and complex data visualization. Unlike linear methods like PCA, it can better capture nonlinear relationships within data. Major challenges: computational complexity remains a significant barrier, particularly for large-scale datasets. Sensitivity to initialization, scalability issues, and parameter tuning also pose challenges that require careful handling. Comparisons with other methods: while PCA is computationally efficient and widely used, it struggles with nonlinear data structures. Alternative techniques like t-SNE and UMAP have gained traction due to their ability to preserve local and global structures while improving computational efficiency. Technological advances and future prospects. Exciting developments include hybrid approaches, deep learning integration, parallel computing, and automated parameter selection. These advancements will likely make salmon mapping more practical and scalable in the future. In conclusion, salmon mapping remains a valuable tool in the world of data science, offering unique advantages in maintaining distance relationships in dimensionality reduction. While it has its limitations, ongoing research and technological improvements continue to push its boundaries, making it an increasingly relevant technique in various fields. And that's a wrap. If you've enjoyed this deep dive into salmon mapping, don't forget to share your thoughts, ask questions, and explore further applications of this fascinating technique in your own projects.